In this lecture, we will focus on the most important features. I'll just remind you that the further away from zero a coefficient is, the bigger its importance. So, by looking at the coefficients table, we will notice that the most strongly pronounced features seem to be the 4 reasons for absence, the transportation expense, and whether a person has children, pets, and education. Note that pet and education are at the bottom of the table, but their weights are still far away from zero. They are indeed important. We can carry on in this way, finishing with the daily work load average, distance to work, and day of the week, which seem to have the smallest impact. Their weight is almost zero, so regardless of the particular values, they will barely affect our model. What about the reasons? We said that the base model includes no reason. But what is the impact of the various reasons? I'll quickly recap what the 5 reason variables stand for. Reason 0, or no reason, which is the baseline model. Reason 1, which comprises of various diseases. Reason 2, relating to pregnancy and giving birth. Reason 3, regarding poisoning and peculiar reasons, not categorized elsewhere. And Reason 4, which relates to light diseases. In the light of this clarification, we can easily understand our coefficients. The most crucial reason for excessive absence is poisoning. Not much of a surprise there. If you are poisoned, you just won't go to work. The weight means the odds of someone being excessively absent after being poisoned are 20 times higher than when no reason was reported. Okay, clear. Another very important reason seems to be number 1, or various diseases. I'd call this the normal absenteeism case. You got sick, you skipped work. No drama. A person who has reported this is 14 times more likely to be excessively absent than a person who didn't specify a reason. Then we have pregnancy and giving birth. I particularly like this one because it's a prominent cause of absenteeism, but at the same time it is way less pronounced than reasons 1 and 3. My explanation for this is, a woman is pregnant. She goes to the gynecologist, gets her regular pregnancy check, and comes back to work. Nothing excessive about that. From time to time, there are some emergencies, but from the odds ratio, we can verify that it's only around 2 times more likely to be excessively absent than the base model. Alright, after that, we've got transportation expense. This is the most important non-dummy feature in the model. But here's the problem. It is one of our standardized variables. We don't have direct interpretability of it. Its odds ratio implies that for one standardized unit, or for one standard deviation increase in transportation expense, it is close to twice as likely to be excessively absent. This is the main drawback of standardization. Standardized models almost always yield higher accuracy because the optimization algorithms work better in this way. Machine learning engineers prefer models with higher accuracy, so they normally go for standardization. Econometricians and statisticians, however, prefer less accurate but more interpretable models because they care about the underlying reasons behind different phenomena. Data scientists may be in either position. Sometimes they need higher accuracy, other times they must find the main drivers of a problem. So it makes sense to create 2 different models, one with standardized features and one without them, and then draw insights from both. However, should we opt for predicting values, we definitely prefer higher accuracy, so standardization is more often the norm. We've gone about this whole exercise like data scientists rather than pure programmers or pure statisticians, so you can rest assured you've seen both sides. Okay, back to the table. Let's interpret one negative coefficient. I'll go for pet. Pet is a continuous variable. Its odds ratio is 0.7. So, for each additional standardized unit of pet, the odds are 1 minus its odds ratio, or 24% lower than the base model. One explanation may be, if you have several pets, you're probably not taking care of them on your own. Not being solely responsible for them implies somebody else can take them to the doctor if something is wrong. Finally, I want to make a note on the intercept. It is used to get more accurate predictions, but there's no specific meaning attached to it. That's why, in machine learning, you can say that it calibrates the model, and you can also call it a bias. Nevertheless, without an intercept, each prediction would be off the mark by precisely that value. All right. For homework, you can try to interpret the rest of the coefficients. Thanks for watching.